And for those of you wondering about the screensaver, those emoji get more and more corrupted with every version of macOS that upgrades, and I enjoy watching them. It's to do with the way Unicode does things. But anyway, so I'm Kate Pearce. Where should I start? How did I get into security? So I actually trained into security, unlike the majority of people you'll hear from. Down at Canterbury, about 10 years ago, they were running a program down there. So I trained my way into it, went to university to do electrical engineering, shifted to computer engineering, shifted to computer science, and then in postgrad, I did security. Went overseas while my wife was doing her PhD, and at that time, I finished up my master's thesis and took a contract job. I used that job to network. I met a bunch of different people, a bunch of different vendors. I used that to get into consulting. About a year later. Then I used it in consulting. You learn really fast. You either survive or you die, but you learn a lot because it's like, here's an IP address, see you in 2 weeks. What am I supposed to find out? I don't know, but write it down. And so I did that for several years, and I, at one point, was running a security practice for Cisco across the Asia-Pacific region. We're doing everything from working on the hardware security of cars, to smart cities, to networks with 500 million users, some truly ridiculous stuff, most of which I can't actually talk about. My better work stories are not stories I can say outside of work. But now I am head of security at TradeMe. I would expect most of you have encountered TradeMe at some point along the way. And my computer, there we go, perfect. So, as you know, TradeMe touches a lot of different aspects of people's lives in New Zealand, and the majority of the adult population are in it. Depending on how you measure it, we probably touch somewhere between 5 and 10% of the economy. A large number of rental listings, house listings, cars, we have a dating site. And then, of course, there's the used and second-hand goods, the new goods, and all of those other different things, and I'm sure I've missed some stuff. Oh yeah, we have a payment processor that processes credit cards. So we do a bunch of different things with a bunch of sensitive data. If we do it wrong, people will die. I'm not joking. With a database like TradeMe, where you have the names, the addresses, verified for a large proportion of our population, if you've got a stalker or an ex after you, if our data leaks, they will find you. This is not abstract. This really happens. Our data, our trust in our user base, if there is a scam, people lose thousands of dollars. Hundreds of thousands of dollars. Security affects people's lives, and we can never forget that. But today, for some reason, I'm here to talk to you about cryptography. That was me at KiwiCon. I'm never going to get a better photo of me. Yeah, that's pretty sweet. I'm going to have to stop showing it at some point, maybe when I'm 90. But yeah, I've had some fun talks and research along the way. Though for those of you that can't see in detail, that slide is full of the word no. I was ranting about something, and yes, that is fire, and it's not a llama, it's an alpaca. I am strongly assured. Do not mix it up. The KiwiCon people do have feelings about that. So yeah, I'm here to talk to you about algorithms and cryptography and some of the more intricate and complex parts of security. But before I get to the detail, really, if you're going to take away anything, take away what is on this slide. I will show it to you at the end. So if you do want to photograph it, you can do it then. But the key point is, as has been reinforced through the whole day, when you make security decisions, make sure they are to use other people's knowledge where those people are smarter than you. Most of the time, other people are smarter than you. Anytime you get arrogant in security is when you make mistakes. But how can you make mistakes if you don't have the background? And so that is what I'm going to try and help you with today, to talk you through some of the key things people make mistakes on, some of the key things that people don't quite get right. That I'm not going to go into any deep details, and I'm not going to tell you here's a specific protocol you should use. Because for that, you shouldn't take my slides, you should look up what the latest best practice is. And it's probably going to have errors in it. If you spot them, good on you. I've also inserted a couple. But on the whole, the principles should be sound. And before I get to the principles of the cryptography and the particularly integrated stuff, let's go with a really, really basic thing that affects nearly every protocol you see online, the three-way handshake. Any of you doing networking will have encountered this until you're sick of it, but make sure you understand it. It's really easy to think you do and to miss it. It can be summed up as, hello, do you want to talk? Why, yes. Are you still good to talk? Great, let's talk. And then the talking intensifies. Or if you're TCP, sin, synac, ack. But it's that, it's talking intensifies. Hello, shall we talk? Sure, let's talk. Make sure consent goes both ways, and then start talking. That is the three-way handshake. And you need to know that for pretty much any networking. Most UDP protocols actually have some form of this in them now too. If you look at Quick, what will go on to be one of the most voluminous UDP protocols, it's effectively HTTP2 over UDP transport pretending to be TCP, but it still has a handshake, a different handshake, but it always starts with, are you there? Yes, great, you can answer me so I'm not just screaming into the void, and then we can talk. The protocols that don't have a handshake are those used for denial of service. The cryptography. And when I was given a topic of cryptography, I was like, oh God. Oh God. That is a tweet that I literally tweeted, because if I use the word crypto, someone's going to go, Bitcoin, or some other weird currency that people are determined to lose money on. But that's not what I'm here to talk about, though I will cover a couple of the principles. I'm not going to make it without saying crypto. See, I just failed. But in the most basic sense, cryptography means, as you will maybe have heard, secret writing. Cryptography. Okay, there's a Latin out of the way. Cryptography is about control. Controlling who has access to what, who sees what, who knows what, who hears what, who understands what, and who could have said that. It's also about economics. This is probably one of the key facts from this whole deck. Cryptography is about balancing the asymmetry of computation, of memory, of knowledge. If everyone has infinite knowledge, cryptography does not work. Gods cannot cryptographically communicate if they are omniscient. Cryptography is about managing asymmetries. I have less ability to break something than you. I have less ability to brute force keys. But conversely, it's also about openness. Because if you're the smartest guy in the room when it comes to cryptography, your stuff has probably already been hacked and the rest of the room is laughing at you. Or they've published a paper laughing at you, the true cryptographer's way. And there's a couple of principles that tie into this openness thing, which I've not put big for a reason. So Kirchhoff's principle, if you're doing cryptography, the secrecy that matters is of the cryptographic key, not of the algorithm. It's also known as Shannon's maxim, which is that the enemy knows the system. So this is, if the enemy got your cryptography machine or your Enigma machine, but they didn't get your code book, it would make no difference. It would be no less or more secure until they got the code book. Very few cryptographic things actually work that way, but that is the basis for a lot of it. A well-tested system, a well-vetted system, is stronger than some guy's great idea. Cryptography also works with a CIA, as with all security, but it's a slightly different CIA for cryptography. Confidentiality of the message, authenticity of the message. Most of cryptography is not an availability, it's authenticity. Is this really what it pretends to be? And is it actually what was sent? And there are a whole lot of different things that go into making this. And I could talk about them. I'm sure you'll probably, should you go and study this, get a lecture on each of these. Maybe 2, maybe 3, maybe 10, maybe a course. And I can talk about these things at the end if someone has questions, but really, this all builds from quite a simple foundation. The basic thing with cryptography is we start with symmetric encryption. That is, you have a message you want to send, a cipher that you send it through. Some plain text is what the message you want to send. You have a key, You put the plain text and the key into your cipher, and it spits out some ciphertext. The reason that's called symmetric is not because of that. It's called that because it also goes the other way, which I'll get to in a second. So if you put an ABCDEF, you put it through a ROT function. If it's ROT 13, you get that. If it's ROT 1, you get that. If it's ROT 17, you get that. The key is what changes the ciphertext, not the algorithm. And as I said, it's symmetric because if you go in the other way, you put in the ciphertext that came out and the key that went in, you get the plain text that you put in the first place. It's exactly the same cipher, the same key in both directions. That's one of the most foundational parts of cryptography. This is the simple case. This is your degenerate base case. But that's not nearly as interesting as when we start getting into things about where we lose or sacrifice information along the way. So, if you have the question, let's say, is this lamp the same as that lamp? No, they're different lamps. But they're both red. Depends on the questions I ask. Is it red? Yes, great. So there are 2 red lamps and there's a red handle. Is it a lamp? Okay, it's down to 2. Is it on the left or the right-hand side? Every question I ask about something helps me to assess, is this the same as something else? You are reducing the essence of something to some little output. So if we take the idea of a person that had a red shirt, in this room, there's about 3 people that could apply to. If you take a number, you're trying to work out, is this number the same as that number without anyone telling you the number? Well, this will narrow out 50% of the entire universe of numbers. If you get down to this would narrow out 14 out of 15 of all the number space. And you can start getting more and more specific. They had a red shirt and green gumboots and a lot of hair. Okay, you're getting a bit descriptive here. And mittens, they have no style, clearly, but that's not in the hash function. But the fact they're a cat. Now, if this cat exists, it is probably a very unique cat. So, this set of questions, if you look at each of these things as a binary decision, it's either a 0 or a 1, depending on whether it matches. Red shirt, yes or no. Green gumboots, yes or no. A lot of hair. Terrible example of a hash function. It's not binary anyway. Do they have mittens? Are they a cat? You've got, let's call it 6 bits of information there to uniquely identify, is it that cat? Or is it something else in the universe? So hashing is where you have a function that you put something into, and it gives you something out. But the difference between hashing and symmetric encryption is you can't go the other way. Because you lose information when you go through a hash function. So if you take the red shirt example, if that's my entire hash function, that could match that guy, it could match that guy, or it could match that guy. All 3 of them are red shirts. Well, more specifically, all 3 of them are wearing red shirts, but only one of them is a red shirt, which you have to watch Star Trek to get. So, some information is lost. You know that whatever you started with and what you got out is a fact. And you do the same thing with a hash function. But what it does do is it gives you some ability to say, is this likely to be the same thing as the thing that generated that output? So you can use it to verify a sense of authenticity, which of course is one of the things you start using in cryptocurrencies, where you take a message X, and then your next message you hash the previous message hash plus your new message hash, and then you continue down that path. But the main point of that is there's a couple of things that come out of this. First of all, you cannot have a later message that is valid if it came before a previous message, because it didn't know what to sign. So there's information feeding through each of these as you go down. And if you came and tried to get this message here produced before this message, you can't, because this message doesn't exist. So it cannot in any way inform the hash. But more specifically, you cannot alter a past message without all of the later ones revealing it, because that chain becomes broken. It's not exactly a distributed ledger, that's a hash chain, but the effect is much the same. A hash says this says something about that, which says something about the previous. You use it to verify some authenticity. Okay, so we can gain security from operations like that, but we can also gain security from operations that are way more difficult to do in one direction than in the other. So a classic example would be mixing paint, or lighting a fire, or shredding a document. It's much easier to do than to work out the original order. This here is on the Wikipedia page if you look up asymmetric encryption. It's one of the very, very few physical metaphors for what is a uniquely cunning and yet really obvious in hindsight way of doing some things which I'm about to show you. So if we take those hash functions, they're an example of a trapdoor function, because you put something in and you get a hash out. But if you have a hash and you want to go back to what came in, that is vastly harder. So the reason these are called trapdoor functions, as I've got up there, is it might be you want to get through that wall, you could get the axe or the hammer, or you could just poke the statue's eye and the trapdoor opens and go through there. That additional bit of information, that trapdoor, is what makes this really, really easy, because it comes down to how you manage the security of that trapdoor, of that key, as to how hard different people find to work in that system. So in maths, that might be factoring numbers. And it turns out this is really, really useful when you come up against a big problem with symmetric encryption. How do you set up communications in an encrypted way with someone that you haven't ever met? You can't share the key because sending it to them, it might get intercepted. Well, that's a meaty problem. And it's one that we've been trying to work out for quite some time. And then it was worked out about 30 years, the NSA worked it out about 30 years before the public did. Really interesting stuff if you look at the archives there. But this is what enables modern commerce. This is what enables a modern internet. What I'm about to show you, this public key cryptography. Now, unsurprisingly, it's called public key cryptography because it has public keys. Now, this slide may seem obvious. Keep your private key private, never share it. Your public key must be shared. You would be really surprised how often people get those mixed up and try and share their private key and keep their public key. I'm not joking. And if you mix them up, the whole system breaks down. So keep your private key to yourself and make sure people know your public key. Because if you keep them both to yourself, they're useless. And if you give both out to the world, they offer no security. So asymmetric cryptography is slightly different to the symmetric cryptography I showed you earlier. So you put something in and you encrypt it with your private key. And out comes something. Now, you cannot decrypt that with your private key. It will not work. You have to decrypt that with your public key. So only you can encrypt, but anyone can decrypt. And in the other direction, anyone can encrypt something, but only you, the holder of the private key, can decrypt it. Now that is really, really foundational, because what that tells us is a couple of things. If something is encrypted with the public key, it can only be read by the holder of the private key. And if something is decrypted with a public key, it must have been encrypted with the private key. And what that means is you can now communicate securely with someone you have never met. How? Well, I'm not going to show you exactly how Diffie-Hellman key exchange works. This is a simplified form. Do not implement this. Do not implement any cryptography yourself, ever. But try to understand and follow this. So, you both agree we're going to use the word peregrine. That's going to be the first part of our encryption key. And then Alice sends a message to Bob's. She encrypts it so only he can decrypt it, saying let's also use the word opossum. Because only Bob can read that, we know that Bob is the only one that could have got that message. And then Bob sends a message back to Alice, encrypted with his private key and her public key, to use the word weasel squawk. So now we know that Bob has sent a message that only Alice can read. She knows that it could only have come from Bob, and only she can read it. So then if you put those together, they now have their key, Peregrine, Opossum, Weasel, Squawk. And only Peregrine was ever revealed publicly. Opossum, Weasel, Squawk was revealed privately. That means, even though Alice and Bob have never met, as long as they trust those public keys, then they can talk. And there is a vulnerability in there. But that's a bit fiddly. When the slides come out, have a play, see if you can figure it out. It's a little bit the way state management works. So, why don't we use public key cryptography all the time if it's great for all of this stuff? Well, it's because it's really, really slow. It also breaks a lot of network tools that are optimized for symmetric encryption. So, you use it to secure the things that really matter, which is your keys. Additionally, as I put there, the more times you use a key, the more chance it could be compromised. So use a key as little as possible. And that's why you protect your private key as much as possible. Use it as few times as possible. And then you've now got your security channel. And this, of course, helps you with your validation. Because not only do we have a way to set up this channel, we can now validate anything that we have in front of us. If I send you something, which is a hash that I have signed, then you know that that hash has come from me and represents a fair representation of a thing. You can now use that hash to check that that thing is legitimate, that it is valid, that no one has changed it. And that's really, really useful. But this all ties together again and to fix that core assumption from earlier, which is how do you do any of this if your public key... Wait, don't you have to share the public key, and what if someone changes it? Which is sort of the same problem we had with symmetric encryption. Well, we could share it in advance, but that means we've met. Well, what actually happens, it's quite useful really, is that maybe we have some friends in common. And then we can ask our friend for our other friend's key, or to verify the other friend's key. And that is basically a public key infrastructure. You got Alice and Becky, I don't know why I chose those names, and Alice, Becky and Elizabeth. Elizabeth's up the top. And Alice asks Elizabeth to sign her key, and then gives that signed certificate to Becky. And Becky can look at that certificate and go, aha, Elizabeth has signed this, I trust Elizabeth, and I have Elizabeth's key. Oh, wait, where did she get Elizabeth's key from? Well, it comes with a web browser, which in the end is how most keys are distributed, either in the operating system, some really foundational common friends that we trust called certificate authorities, or sometimes in the operating system or web browser. And, that's not ideal, but it's a great deal better than not being able to talk with people you've never met. And this is why self-signing is bad. So, if Alice sends a note to Becky saying, here's my key, signed Alice. Wait. There's a problem there because what if someone else is in the middle? And they're like, hi, I'm going to send her one and I'm going to sign it Alice. If you don't already have Alice's key, you cannot verify her sending you a certificate with her key signed with her key. And that is why self-signed certificates are bad, because they mean that anyone can jump in the middle. Because they've broken down the foundational assumption here, which is that you have a common friend, a common trust path, a common root of trust. But even all of this breaks down if the numbers that are used for these keys aren't random or guessable. And it turns out this is also a really, really hard problem. A really hard problem. But there are things we can do. Like wait for the slides. Come on, slides. Never trust Google Slides. Never. There we go. Because computers are terrible at randomness, except this one. And they do exactly what they're told, except this one. And except this one, when you give them an input, you get a predictable output. Well then, how do you use a computer to generate a key which is not predictable by a computer? Well, you might think as a developer, I'm just going to use a random number generator. Nope, no biscuit, nope. Computers do not have true random number generators, in most cases. You might think, well, I'm going to use a pseudo-random number generator, PRNG, because it's all the same thing, right? Well, nope, still not good enough. Because a pseudo-random number generator can still be predicted. And then you think, what next? Well, then you get into your acronym soup and you decide, I'm going to use a cryptographically secure pseudo-random number generator, which is like a pseudo-random number generator, which is like a random number generator, except a lot more complex. But it's also a great deal harder to predict and to model. So whenever you are coming up with a security-relevant random number or key, use a secure random number generator and not java.random. You laugh. I have seen that so many times. It is very easy when you're a developer to just do what is the most easy and natural, the same way you solve any other problem. But security problems are not the same as other problems, but if you do solve them right, you get a biscuit. Or a biscuit emoji. Use secure random number generation. If you're not sure, use a secure one and fix it later. Don't start with an insecure one and decide to fix that later, because it may be too late. So you've got all this randomness from your computers, and as I said, don't ever use a normal random number generator, and also don't use the wrong data type. This is a really interesting story about random number generation and data types. I'll quickly give it to you. So in Bitcoin or other cryptocurrencies, you need a very long private key. That is your wallet. That wallet is somewhere in the order of hundreds of bits, hundreds to thousands of bits. But it turns out that if you use a weak random number generator, you can guess what most people's wallets will be if they used that. But more specifically, if they decided to generate that and put it through an integer, which is 32 bits, and then put it back out, you've now got a key that is only 32 bits long. And it turns out there are people watching the internet anytime a key comes up that can be factored in the integer space, and within very few seconds, wallets are emptied. Why? Because they are not using randomness correctly, because they are simplifying it. And simplifying that randomness really comes up in another point, because hashing doesn't matter if you can predict what goes in. You don't need to guess the key if you know that it's one of 10 values coming in. And where this really matters is with passwords, because hashing doesn't provide privacy, it doesn't provide secrecy if you can predict the input values, and you can test them rapidly. And we can test them at somewhere between millions, billions, to tens and hundreds of billions of combinations a second. Which if you're using anything from A to Z, 0 to 9, and it's 8 characters, that's like a minute. Doesn't matter what your password is, it can be tried in that time. So never, ever simply hash secrets or things with predictable values for a security or privacy purpose. And what that's likely to mean is these sorts of things. You will often if you're out there, see people hashing things for privacy. If you hash a phone number for privacy, I can test them all in about 4 seconds. So it's not really that private. Same with a username. Well, maybe that's not private, true. But what's happened is they've probably put it in 4 million other dumps, other password dumps, and so I'll just pull out all the usernames from there and try them. I can predict what they will be. All of these things, IP addresses, MAC addresses, phone numbers, even emails. If someone can get a list of what it probably is going in, do not hash it for security. But if you're not hashing it for security, what are you doing and how do you store it? Passwords are a particularly interesting one that I want everyone to be very careful with because they're easy to mess up. You do not ever need to store users' passwords, ever. All you need to be able to do is to know if the one they tried is the same. Think of my hash thing earlier. You only need to know, is that the same cat with gumboots or not? You only need to know, is that password the same? You do not need to know what it is that it actually is stored. You just need to know, is it the same? Is it correct? And that is where hashes come in. And I put the word bad up here so that no one takes a picture of this slide and implements it. I will warn you that if you do a lot of talks, that is something you have to watch. You will put up bad examples, someone will implement it and bring it to you for a treat. It's happened to me. So, yeah. Side note, whenever you put up slides of bad examples, put a note on them. Or they make it to Twitter, and then the trolls come in, and you're like, I wasn't. Anyway, password hashing means that even if the database is compromised, the user's password doesn't get out. But you don't use a normal hash for a password. You presume attackers will compromise them. So you make sure that what goes in is not overly simplified. You don't change the case. You don't cut it in half and make it short like our NTLM did. You use a slow, annoyingly complicated hash. You do not ever optimize password entry for performance. It ends very badly if you do. This is the one place I will give you specific technical recommendations on my slide. Basically, anything other than the ones on that list is bad. Do not. And never use an MD5. Never use a SHA-1, a SHA-256, a SHA anything. Ever. Never, ever use those for passwords. And you will find people who have done this, and you will make sure that they know, never, ever use this for passwords. And you will help them fix that. But it's not enough just to use a complex hash this slow. You need to make sure that you also make sure that if the users have the same password, they don't have the same hash value. So someone can't find all of the users with the password with the same hash. And you do that by making what's called a salt. You give every stored password a unique random value that you throw in when you test the password. And that means that no one can test all of them. They have to test each one individually. So rather than testing a password and seeing does anyone match it, they have to try it. Test a password, does this guy match it? Test a password, does that girl match it? Test a password, does this NB match it? You have to go through every single one, and it slows them down millions of times. And as I said, I didn't mention a whole lot of protocols, did I? And there are a whole lot I could have mentioned, and a whole lot that at various points you may need to know. But the thing you need to know above all else is what is it you are trying to achieve? What are the security promises you are making? These are just some of the protocols, and they will change. Some of them are new, and some of them are like 40 years old. I don't even know how old ICMP is. On the other hand, HTTP 3/quick was ratified by the IETF a couple of months ago. That's going to be a whole lot of fun for security testers, I tell you. As I said, here's the thing. All of these things combine together into the algorithm. So SSH is this public and private thing, but you don't use certificates. You just presume they have the key. HTTP/HTTPS is just the thing I did with the certificates, with a little more nuance on top. And Bitcoin and cryptocurrencies are just that hash chain going down the slide that I had with a bit more stuff. But at heart, they are all built on these same concepts. Control, economics, and openness. And as I said, there are a whole lot of other things I could have covered. These are all fascinating things with all sorts of interesting things, but every one of these would detract from the key point, which is this stuff. Do not ever make your own cryptography. Use one that's been tested by someone else, someone much smarter than you, preferably many someones. Use a secure random number generator. Use a secure implementation. Don't implement your own version of someone else's protocol either. That usually ends badly. And when you do use someone else's implementation of protocol, use the public recommendations. So use the secure things. Don't use the things that people say not to use. When you store passwords, use slow hashes, strong hashes with a salt. Just, don't ever do your own, because you think you're right and then someone will make you wrong very dramatically. Now, if you do want to do your own, okay, if you want to go down the 20-year path of going through academia, becoming a professional cryptographer, that is absolutely a thing you can do. I hope you like people telling you you're wrong, because that is cryptographers' favorite thing. The things that will matter to you are picking how you use the things you have in front of you, how you manage your keys, and how you distribute your keys. Everything else is details. Thanks.